It's my pleasure to introduce the first speakers for the morning. That will be Paolo Bombelli and Gianmarco Iodice. Paolo Bombelli is from the University of Cambridge. His interests lie in translating the principles of photo, bio, and electrochemistry into practical applications. He will start the talk this morning, and then he'll be followed by Gianmarco, who is the tech lead at the ML group at Arm. He is behind the development of the Arm compute library, and he leads the ML performance optimization team for the Arm Cortex-A CPUs and the Arm Mali GPUs. The talk is Powering Machine Learning Applications on Arm with Algae. Paolo, all yours.
Thank you very much. Good morning, everyone. The first part of this talk is involve elements of plant biology. So for this reason, I decided to give a bit of introduction based on the assumption that not necessarily plant biology is very popular in this audience. So let's start with something that I suspect doesn't need too much introduction itself, which are plants. So we all know how they look like, and more or less we all know what they do. The element that is important for me to bring to you today is to grow, they consume two elements, water and light, or if you prefer, photons. And those two elements are net consumption. The second element that I want to present to you are algae. Again, I can really stay here for quite some time telling you elements about algae, but the only thing that I really want to, the way that I want to summarize what algae are, they are sort of aquatic plants. So they are plants living in water. This is not completely correct because there are actually algae living on soil and plants living on water. But generally speaking, plants are terrestrial and algae are aquatic. And one of the remarkable difference between plants and algae, so plants are always multicellular organisms, whereas algae, you can find unicellular algae. For example, here you can see Chlorella vulgaris, which the body is a round cell, and the body is about 5 micron in diameter. The next element are cyanobacteria. Again, even for cyanobacteria, I can really spend probably too much time telling you elements. But something that, in the way that I like to summarize, cyanobacteria are old algae. In fact, algae are evolved from cyanobacteria in the same way that plants are evolved from algae. And cyanobacteria, they only exist as a unicellular organism. They don't form multicellular. They can form colony, but they remain like an aggregate of many unicellular organisms. But there is something that is in common across all those organisms. They all operate based on photosynthesis. So photosynthesis is a quite broad umbrella under which there are hundreds of different metabolic steps. And each alga, cyanobacteria, or plants does photosynthesis in a bit different way. But there is one step that is very much common for all of them, on which all of them they operate. And this step is a very early stage in the process of photosynthesis, and this step is called water photolysis, which actually means breaking water using the energy of light. And if you break water using the energy of light, you end up generating three products. One is oxygen, and the 21% of oxygen in atmosphere is actually coming from this simple reaction. And the other two products are protons and electrons. Physiologically, plants, algae, and cyanobacteria, they use those proton electrons for organicate CO2 into organic carbon. But in a sense, proton and electrons is a form of charge separation. Therefore, if we find a way to take some of these electrons, channel through an external circuit and recombine to the proton, maybe we can generate electricity from photosynthetic organisms. And actually is exactly what we're doing here. So the idea that I just described to you, the incarnation of this idea is displayed in this diagram. So the green layer represents either unicellular algae or cyanobacteria. When they harness light, they use it to do what I said just a few seconds before. They use it to do water photolysis. The electrons are actually not able, electrons, they don't float in water. Electrons require the electron carriers. The intracellular electron carrier, there are quite a few. The most common one is the NADPH. And NADPH carries electron around the cellular body, but is now able to pass the plasma membrane, which is the barrier that delimits the cellular body of the cell. But there are ways to actually extract those electrons. There are electron carriers that can go through the plasma membrane, for example, phenazine, or you can have electron carriers sitting in the membrane. There are transmembrane protein like the ferroreductase and the NADPH oxidase they act as bridges. They take electrons from the intracellular space and they deliver electrons on the extracellular space. So the phone can be passed from the photosynthetic organism to an electric conductive material, and technically speaking, an anode. And the way that this is occurring a certain redox potential. And this is the anodic redox potential. Then if we connect the anode through an external circuit through which electrons can be moved, then we can deliver those electrons to a second electrode called cathode. And at the cathode, thanks to a catalyst, we can recombine electron and proton. The difference in redox potential between the anodic and the cathodic direction is the potential that drives the circuit. And the number of electrons going through the system, going through the external circuit, is actually proportional to the current that we can generate. So this is the general idea. Point is, how much current can we generate? So in this example, this prototype, which is about 60 millimeters tall, has an internal volume around 17 centimeter cube, is able to generate something in the region of between 2 and 4 microwatt per centimeter cube. This is not the best performance that we can get, and neither they are the theoretical limit, but they are real and consistent performance that we can claim right now. So what can we power with this? So to answer this question, we need to define the domain under which this technology can operate. The bad news is that unfortunately I don't really think we can power elements in the domain of hundreds of watt, kilowatt. Well, in principle we could if we have like couple of football field covered with this technology, but this, I'm not here proposing you to do this. So the idea is having a reasonable scale. What can we power? Definitely not large items that require a lot of electrical energy. I'm ruling out. Not today and probably not tomorrow. The good news is I truly believe we are going to able to power something in that required a watt or few watts. But right now we are able to power microelectronics. And I truly believe this is a good news because many of you work with microelectronics. So the point is, can we try to combine the two elements? Can I power some of your machine learning? We already have a few examples of devices that we end up powering using algae or cyanobacteria. Digital clock, small LEDs flashing, and more recently we were able to power an Arm Cortex-M0 for about 6 months, actually longer than that, but we published the 6 months, in a domestic environment under ambient light. I'm stressing those 3 elements, 6 months, ambient light, and domestic environment, because if we want to really look for a practical application for the generation of electricity from algae or cyanobacteria, we need to operate on real environment. Lab is great to prove the concept, but then at some point we need to be more real. And that was really real. I mean, we did in the way also because some of the experimental work was done during the lockdown. So the domestic environment was my living room. So the next step is actually, let's try to power some machine learning. So we are building up like a customized device that will be located on a canal in London, floating on the canal. And you see some of the component forming this device. And to do what? I pass the stage to Gianmarco.
Okay, I hope you can hear me. Thanks a lot, Paolo, for the introduction. And in this second part, I'd like to start from the overall goal. What is the goal? The goal is to make a contribution to a sustainable technology for thriving healthtech communities, but with an eye or focus to low and middle income countries. What does it mean? It means that this technology needs to have a low impact on the environment, but also be affordable, needs to be low cost. And this is light of also of the panel discussion that we had last year here at tinyML EMEA. We have discussed a lot about the cost. In some countries, devices also of £20 or $20 or 20 euros is too much. So we need to think about it. But I have also attached to this goal a quote from a book I'm reading. There is a continuation to this quote at the end of this presentation. Because every time we see big environmental problems, we think, well, we need a cloud, we need an infrastructure. In other words, it means that we think very big. And we think that a solution has to be big because the problem is big. Is it true? So here I'm not going to talk about the solution that's going to solve all problems in the world, because we cannot solve all problems. Maybe some ideas and maybe trying to inspire you to build something for the environment. So what can we do with an algae-based battery, like what Paolo described before? Well, we cannot do everything, okay, because the power budget is limited. But we can do definitely something. We can monitor the environment through many sensors. And this is actually the application we were thinking. So when you need to, we have a river, you want to monitor the quality of the water, well, you need a lot of sensors spread over the river in order to get this information. And definitely the algae can help because algae can be collected everywhere. You don't need to go in a specific country to get it. So in theory, you can get the algae from that place because as Paolo mentioned before, in London we took the algae directly from the canal. So this is meant for rural areas in particular, where this small power budget can actually provide an important information for the people living there. At the bottom, there is also a model of this, let's say, natural battery. How does it work? In simple terms, during the day and during the night, it continuously provides more or less a constant power budget. More or less because, of course, you have a fluctuation during the night. But the beauty of this technology is definitely the fact that it incorporates an internal battery, a natural battery, so that basically the algae survives also during the night and can produce electricity, also without light. But now, to the overall goal I gave you at the beginning, I'd like to attach other two things, which I really believe are very important. While I talk about sustainability, I talk about low and middle income countries, but I'd like to also add other few important things. We like to demonstrate that people, regardless of their expertise, has the power to address environmental challenges using not tomorrow's technology, but today's technology. Because this is actually what makes the technology scaling. I mean, you can have the best idea in the world, but if only few people can do it, it's going to be very difficult. Okay? So we want to demonstrate that everyone has the ability to do it in a sustainable and, as I mentioned before, in a very affordable way. How? We have powered the first machine learning application with algae using an ARM-based microcontroller. Today's microcontroller, so not something we're going to see in 3 years' time. Because the project is actually this. We want to monitor in the weather conditions and the water quality with tinyML. Where in the River Thames, in this particular case, because it's close to Cambridge, I mean, we are all based there, but using the native algae of the river. Someone can ask, well, do I need internet connection here? Maybe not, because in some scenarios, you don't need internet connection at all, because probably what is very important is awareness. You can definitely build something smart that does not require internet connection, because the information you want to deliver is to the people who are living there, just to make it aware that if the water is polluted or is it safe to swim there. Awareness. So let's not think too big. Let's think small. So what are the ingredients? So here the power budget is defined. So we have a range of 20 milliwatt, more or less. But another constraint is on the voltage range, because unfortunately, not always we can have the 3.3 volts that we usually have on microcontroller, for instance, based platforms. The power budget will influence the choice of the device and the sensors. But the other influence is going to be on the machine learning deployment framework library. Okay? As you can imagine, you define the device, and only once you have defined the device, you will need to decide which framework to use. So about the device selection, I mentioned we want to make it easy. And our choice was for microcontroller. Why? Because user-friendly, many people know what a microcontroller is, are everywhere, and that is our preferred option. The microcontroller must be low power, because we are talking about 10 milliwatt, so which is definitely an important power budget, but it's not an immense power budget. And the microcontroller needs also to operate between 1.9 volts and 2.7, because that is more or less the range that we can expect, especially from what has been built on the River Thames. What do we expect from a microcontroller with this power budget? now, not tomorrow. So now, well, probably the floating point unit is not an option, so we are not going to have a floating point unit. So keep in mind that in terms of program memory and RAM, well, most of the time you can find a program memory or ROM of 32 kilobytes and an SRAM of 8 kilobytes, so definitely small. You can also find something slightly bigger, but this is more or less the range that you can find. Low CPU clock, well, it usually is around 10, 16 megahertz, and that's it. When you build something like that, you also need to consider that in your system, everything will contribute to the power consumption. It's not just the microcontroller, also the sensors and other things. So keep it at minimum, not over put other items on the board. What are the challenges? Well, challenges are what I mentioned earlier. So most of the microcontroller boards, they need a voltage range of 3.3 volts or higher. And that is absolutely a limitation for this kind of application. So most of platforms operate in that field. So what does it mean? It means that we need to implement or develop from scratch a board. Oh, how can I build a platform from scratch, and how difficult it can be? Well, what I can tell you is definitely easier than what you think. But of course, if you have a development board, use it, because that is the easiest way to definitely have up and running application. But if you cannot, don't worry, because thanks to the open source community, there are plenty of materials, and you can definitely learn, trust me, to build your own board with few components. Of course, something to keep in mind when you decide a microcontroller, if you're just prototype, well, remember that soldering could be a big challenge, so try to select a microcontroller where the pins on the chip are easy to solder. Sensors consideration. Well, the power budget is limited. The voltage range needs to be still around 1.9, 2.7, but we cannot power all the sensors in the world because, for instance, vision sensors are not probably suitable for this. We have a limited number of sensors to use, and these are just a subsection. The big challenge is the fact that most sensors or boards do not operate with 3.3 volts, so we have a limited number of sensors that you can connect. I'm speeding up, but I would like to spend just a few seconds on this slide, which is the machine learning deployment framework, which depends on the target device. But since you're targeting a microcontroller with a reduced program memory, one feature I really recommend is a machine learning framework with ahead-of-time capabilities. Don't think about a framework where you need to load the model because everything will have an impact to the program memory utilization. So try to have, for instance, compile your machine learning deployment ahead of time so you can save the program memory and leave the the rest of the program memory to something else. That was our solution. It cost just around £3. A microcontroller, this is not the only solution. There are many solutions you can build. A microcontroller, a simple adapter for soldering and having the external pins to put on the breadboard, is on the Arm's boot, by the way, which these capabilities has 32 kilobytes of program memory and 8 kilobytes of SRAM. How you can program? I mentioned that it needs to be affordable, and what I can promise, you don't need a laptop. In countries with small middle incomes, we can use a Raspberry Pi directly. You can use that for programming, and with programming I mean writing C code, and you can also flash the board directly. And this is what we have used. We didn't use the laptop. We used directly the Raspberry Pi. So what we have, these are the two last slides. So we have at the moment deployed a very simple test case for a machine learning model, but in particular to thank Pete Warden and Daniel Sutanaki for their contribution to the open source community. We have deployed the machine learning model that produces a sine wave just to demonstrate that it's possible to power machine learning applications on these tiny devices. And here I have reported some numbers, but probably the most important one is the current consumption, which is around 1.8 million per, which for the budget we have is absolutely perfect. I skipped this. Of course, it's still in progress, the project, so it's not finished. I really hope next year to have to present something else about this. But I'd like to leave you with a new acronym where we have talked about it, the natural artificial intelligence of things. So the device that does not need internet connection and but can be powered with only the natural power sources. And this is the first use of this acronym for what we know, and here tinyML EMEA. Thanks, everyone.